Now we are going to start with the Maxwell's equation in module 3. Before going to start with Maxwell's equation, we will see the introduction to vector calculus. Now we define here now what is a scalar and vector. Why we are discussing scalar and vector is we need to associate the scalar to the fields. So before going to the field, we should know what is a scalar and what is a vector products. The scalar dot product of two vectors A and B making an angle theta between them is A dot B is equal to AB cos theta, where A and B are the magnitudes of the vector A and B. That means a scalar product, if there are two vectors A and B making an angle theta between the two vectors, then scalar product is given by dot B, that is AB cos theta. Next, the vector cross product of two vectors A and B making an angle theta between them is A cross B, that is AB sin theta into n cap, where A and B are the magnitudes of the vector A and B. Now if you look at this, A dot B is a dot product and A cross B is a cross product. Now we see what is a field. Field is a set of functions of coordinates of a point in space independent of time. So field can be expressed by a scalar or a vector. Next we see what is a scalar field and what is a vector field. Scalar field is the region in space in which a scalar quantity has a unique value or a magnitude at every point. Example, electric potential and temperature. What is a scalar field? The region in space in which a scalar quantity has unique value or a magnitude at every point is called as a scalar field. That means scalar quantities associated with scalar fields. Now next is a vector field. Vector field is a region in space in which a vector quantity has unique magnitude and direction at every point. Now for example, gravitational field intensity, electric field intensity, which are in 3-dimensional, and 3D magnetic field intensity, etc. are the vector fields expressed by the three components of vectors along the three coordinates. So vectors can be associated with vector fields, scalars can be associated with the scalar fields. Next is an operator del. We see in mathematics the operator del is used to call as del del. When this acts on a scalar quantity, it indicates to differentiate that quantity. Operator del is given by dou by dou x of I cap plus j cap into dou by dou y plus k cap into dou by dou z, where I, j, k are the unit vectors along x, y and z directions. If phi is a scalar function, then del phi states that del operates on function phi. So del is an operator operating on a function phi, which is a scalar quantity. Phi is a scalar quantity operating with del, which gives del operates on phi. It is read as del operates on phi. Now del can act in three different ways, namely, when del acts on a scalar function phi, then del phi is called as a gradient. When del acts on a vector function f, then dot product del dot f is called as a divergent. When del acts on a vector function f, then the cross or a vector product del cross f is called as a curl. So in order to understand this dot product and cross product, I have given introduction what is a dot product and what is a cross product. So del is operating in three different forms. Del operating on a scalar function, and also del operating on another vector function as a dot product, and del operating on another function which is a cross product, then del cross f is called as a curl. So gradient, divergence and curl are the three things which del will be operating. Now we will see what is a gradient. Gradient of a differential scalar point function phi of x comma y comma z is defined as grade phi is equal to del phi is equal to I cap into dou phi by dou x plus j cap into dou phi by dou y plus k cap into dou phi by dou z. If phi is a scalar point function, then del phi or grade phi is a vector point function. That means a scalar quantity can be made into a vector quantity by operator del. If del operates on a scalar function, it becomes a vector point function. For example, E is equal to minus del V. Here E is the strength of the electric field and V is the potential. V is a scalar quantity. It is when the del is operating on a scalar function, you are getting a vector function. So this is called as a gradient. Now divergence of a vector point function. If E is a vector having x, y and z is a differentiable vector point function, then divergence of E is Ex into I cap plus Ey into j cap plus Ez into k, defined as divergence of div E is equal to del dot E. That is, it is a dot product. Del is operating on a function E with a dot product. Del dot E is equal to I cap into dou by dou x plus j cap into dou by dou y plus k cap into dou by dou z of a dot product. This is all one del operator, dot with Ex of I cap plus Ey of j cap plus Ez of k cap. So div E can be taken as, because I dot I is 1, j dot j is 1, k dot k is 1, and rest of the cross product dot I dot j goes to 0, j dot k goes to 0, k dot I goes to 0. Therefore, div E will be given as dou Ex by dou x plus dou Ey by y, dou y plus dou Ez by dou z. Here, this is the div E. The divergence of a vector function is a scalar function. Physically, divergence of a vector field at a point is a measure of how much the field diverges or emanates from the point. That means is a measure of how much field it is diverging. How much field it is diverging means it is moving away. Converging means it is moving into it. Diverging means it is going away. So what is the physical significance of divergence is it is a measure of how much field it is coming out. Diverging, it is going out from a single point is the physical significance of a divergence. Next is curl of a vector point function. If vector h having components of x, y and z is differentiable vector point function, then the curl of h is hxi plus hyj plus hzk is defined as curl of h. Curl means cross product. So curl of h is given by I cap into dou by dou x plus j cap into dou by dou y plus k cap into dou by dou z cross with the vector function hx into unit vector I cap plus hy into I j cap plus hz into k cap. Here hx, hy, hz are the components of h along x, y and z axis. If you do the cross product, we all know it is a cross product means curl of h means curl with a del cross h. Curl of h means del cross h is called as a curl of h, which is equal to, it is in the matrix form ijk dou by dou x, dou by dou y, dou by dou z, and h along the hx is a component along x axis, hy and hz. So physically the curl of a vector field at a point is a measure of how much the field curls or circulates around a point. The curl, as the word indicates, it curls. It curls. It is the amount of field circulates. It is a measure of the field curls. How much the field is curling or circulating around a point gives you the curl of a vector point function. Next is we are going to deal with different types of integrations like linear, surface and volume integrations. A line or a path integral is an integral of a function along a path or a line. For example, a line integral of a vector field is the amount of work that a force field does on a particle as it moves along the curve. Now you can see the figure here. It is a line integral or a closed path. This line integral is an integral of function along a line or a path. Consider a vector field A and an small element of length dl along the path PQ at M. If you look at the figure there, along a path PQ at M, and theta is the angle between A and dl is element, then the line integral along the path PQ. If you take a small total path PQ, if you measure at a small value and if you integrate it over the line, you can get the value of it. So the line integral along the path PQ is equal to integral of lower boundary P to Q A dot dl. For a closed path, the line integral is integral of for a closed surface A dot dl. The symbol for a closed counter line integral is integral of closed loop. The line integrals are used to find the potential difference 2 points in an electric field. So this is the use of a line integral. Why do we want to do line integral is in physics we are going to get the potential difference between the 2 points in an electric field. So we use a line integral. Next is a surface integral. It is a definite integral taken over a surface. Consider as if you look at the figure over there, it is over a surface. Previously we have seen for a line. Consider a small area ds on a surface of area S surrounding point M in a vector field A. Let n cap be the unit vector normal to ds. And n cap represents the area vector of ds. Then the surface integral over the entire surface is surface integral of A ds. The surface integral gives the net outward flux of a vector field through the surface. The symbol for surface integral of S. You write S, it becomes a surface integral. The surface integral for a closed surface is integral of, you can put a closed surface and put S, A ds. A and ds are the two vectors. The surface integrals are used to find the net electric flux through the surface in an electric field. So for a surface integral is nothing but taken over a surface. Next is a volume integral. Volume integral refers to the integral over a 3D domain. Volume integral are important in physics because to calculate the flux densities, volume integrals of charge or mass densities gives the charge or mass at that volume. So volume integrals are very important to calculate the charge density or the mass density depending upon the volume of a surface. Consider a volume V distribution in which the charges are distributed continuously. Let a small volume dV around a point M inside the charge distribution. If rho be the density of the charge at M, which is a scalar quantity, then the net charge in the volume is given by volume integral of over a closed loop volume integral rho into dV or integral of S rho dV. The volume integral symbol is integral of closed loop V. This is called as a volume integral. Thank you.